Hello, my name is Paul Wilson and I'm here with my colleague David Clement, and we are the Engineers in Control. This is the 7th talk in our series Control Systems 101. In talk number 7 I am going to introduce some very important concepts for control systems engineering, and that is the concept of complex numbers and the complex variable S. So we're going to be looking today at complex numbers. I was amazed to find out recently that there are students in the second year of an engineering course who have never met complex numbers, either at university or at high school. I can't imagine how on earth they got into an engineering course without having met this concept. The reason it's surprising to me is because complex numbers is such an incredibly useful concept. Complex numbers are bizarre, but it is also a very clever trick of mathematics, and in control theory you can't do control theory without understanding complex numbers. So you may or may not know that it's impossible to have the square root of a negative number like that, right? So what are we going to do? Well, let's be like Alice and let's enter the realm of Wonderland, and if we go into Wonderland we can imagine having the square root of -1. Imagine that it is possible. Okay, so if we're going to assume that it's possible and that we can imagine this, we can use it as a mathematical tool. Now the mathematicians just to be contrary use the letter I. In engineering we can't use this. I means electric current. So engineers use J, and we're going to stick to J from here on. So J equals the square root of -1. So J squared equals -1. J cubed equals -J, and J to the power 4 equals 1. And that's the basis of the use of complex numbers. Now the reason complex numbers are so useful is because in engineering we have a lot of problems with two-dimensional vectors. If you don't know what a vector is an entity that has two independent components. And it's the independence of those two components that's important. So we have one thing that's got two independent components, and a good example of this is a married couple. It's an entity, but it has two independent parts. It has a wife and the husband. They're independent people, but they make up the couple. And that is an example of a two-dimensional vector. Alright, in engineering we have lots and lots of these, and we draw it this way. Alright, so we can call that X and Y, and we might have a point here, right, that is a vector. And it has two parts. One part, another part. And so we might have this as a 1, and we might have that as a 1. In the case of a married couple, let's put the wife down here and the husband there. We have the wife and we have the husband, and together they make the couple. And that is a two-dimensional vector. Now in engineering we have lots and lots of these, and generally we will draw the vector like that. It's a really useful concept, and in particular in control engineering it's a very important concept indeed. It works, the mathematics kind of works, doesn't always work perfectly, but the mathematics works well enough to allow us to solve difficult problems. Now in control engineering we have one circumstance where we use a two-dimensional vector, and it's really important. And we call this vector complex frequency. And we give it the letter S. And this is a variable. A bit like X or Y, but it's a complex variable. Okay, so we've got two components. Component 1 is the real part, and it is sigma. Component 2 is the imaginary part, and we give it the Greek letter omega. So S equals sigma plus j omega, and the j, square root of -1, indicates that that's the imaginary part. So that's the real part and that's the imaginary part. Now what sigma represents gives exponential curves. So always when we have a sigma we end up with an exponential curve like that. We can have different shapes of exponential curves, but it's the sigma component that gives us that. Now j omega gives us sine waves. So the j omega part gives us responses that look something like this. And we can have lots and lots of them. We can have bigger ones like that. We can have little tiddly ones. These are the sine waves. So let's just repeat that. The real component part of this variable S gives us exponential curves. The imaginary component j omega gives us sine waves. And all of our responses in control systems consist of sine waves and exponential curves all added together. And algebraically the curves just add up. So that is why it's really, really useful. Thank you for listening to talk number 7, and I hope you will join us for talk number 8. The engineers in control are Dr. Paul Wilson and David Clement. You can find out more about us at www.engineersincontrol.com. Unless explicitly stated, all content in this video is original and is copyright 2022 by Dr. Paul Wilson and David Clement. All rights reserved.